Please welcome developer advocate from Google, Fred Sar.
Hello everyone, konnichiwa. Welcome to Debu Festo. Today's talk is about Google App Engine, about distributed memes. Memes are ideas or concepts or ways of thinking about building an application to make it scalable and to take advantage of App Engine. So this is our agenda today. I want to start off with asking just a few questions to gauge the audience. So how many people here, please raise your hand, have used App Engine already? Okay, quite a lot. How many people have never used App Engine? Never. Okay, few. So the start of the talk will have some introduction of cloud computing. So for those of you who have not tried App Engine, we have some introductory slides. I want to do a very quick demo, if I can, to show you how easy it is to get started running an application in the cloud. I want to talk about the community, and then we get into the main part of the talk, which is distributed memes or distributed ideas. And I'll use social applications as examples. So what is cloud computing? If you hear a lot of people talk about it, a lot of vendors have solutions, but cloud computing can mean different things to different people. And basically the way I like to think about it is 3 layers in a stack. At the lowest level, we have infrastructure as a service. That is basic computing hardware where you buy a server that sits in a data center and you install the operating system. You install a database server, you deal with patches, you deal with scalability, you do everything except for the physical machine. Then one layer above that we have platform as a service, and this is where Google App Engine sits. So it's a managed platform, scalability is built in, there are many APIs to use, and you can focus on the value add of creating your application and making it work well for your users. You don't have to deal with an operating system or other complicated issues. And then that top layer, software as a service, that's where you are building an application. When you write software and build it in the cloud, you're creating software as a service for your users. Now, the first kind of wave of cloud computing was this infrastructure as a service. And the value proposition there was we give you network connectivity, we give you power, servers of course, and cooling. And everything else is your problem. So the hosting company, they do all the easy stuff. They have thousands of servers, they put them in racks, they plug in network cables, and they're done. Now you have to install your operating system and manage it and patch it and keep it up to date. With App Engine, we get this platform that's managed. So we like to say we wear pagers, that is mobile phones. When something goes wrong, we go and fix it. You just worry about your application. And when we set out to build Google App Engine, we had kind of 3 goals in mind. We wanted it to be very easy for you to build applications. We wanted it to be easy for you to maintain those applications in the cloud. And we want it to be very easy to have those applications scale up. When you need additional capacity, when more users come, when your site sees more traffic, we want your application to be able to scale. So everything that we've done to build App Engine has these 3 things in mind. And it's really easy to get started. Deploying an application is a matter of clicking a button, waiting just a very short amount of time, and then the application can be live on your domain. So with that, I want to show you a quick demo. And let me just switch over to another display. And what we're going to do here is this is the Eclipse IDE, the open source IDE, and there's a Google plugin installed. And if you have a watch, I'd like you to look at the time and see how long this takes. So starting right now, I'm going to create a new application. Let's call it Tokyo. And we create a default package, Google Tokyo. We're not going to use Google Web Toolkit in this demo, only App Engine. And this will create a default template application that we can use, kind of a hello world. And you see that right here. And we can, in fact, just run that right here. But in the meantime, let's see. Let's get a browser up. Localhost 88. And there's our web server. This is the local SDK web server, and we have a little servlet that says Hello World. And you see that right here, the servlet, print Hello World. So let's deploy our new application to the cloud. And this is where the 60 seconds comes in. That's all it takes. So I've already created an application ID, and I enter my Google username and password, and I hit deploy. Now imagine if you had to, you just built this sample application with this servlet, and you had to configure a new web server, and you had to maybe configure a database server. You had to create a database. You had to create ERD. You had to test everything. You had to maybe create a backup server. All these things that you have to do. But we're already done. We just deployed to App Engine, and now in the cloud, we have our same application working, less than 60 seconds, and there's our servlet. So we can make changes, we can deploy, and it's very, very quick. So that's what we mean when we say easy to build, easy to maintain. So let's go back to our presentation. So Google App Engine is all about kind of leveraging our platform, taking our services and our APIs and our infrastructure and using that so that you can better serve your customers. Now the platform today is about 250,000 developers and growing, 100,000 applications, and each day we serve around 250 million page views. So that's all on this shared infrastructure that you can take advantage of. There are many concepts around App Engine. This is a little world map created from the App Engine wiki page. And you can see some of the concepts here, some of the languages, like JRuby's on here, of course Python and Java for the two runtime environments. And this little word map was actually created with an App Engine app called Wordle. So you can build these own clouds. Now, some of the applications that are really popular in App Engine that I'd like to talk about today are social applications. These are the applications that require a lot of scalability because a lot of users can come in quickly. These applications, they are very viral, and so you very quickly run into millions of users. In fact, social, or BuddyPoke here has today over 40 million users running on App Engine platform. Something a little closer to home, of course, Mixi. There are many applications, Mixi applications that run on App Engine, and this is just one example, the Mixi Christmas app. I chose this example because in the first 2 weeks after launch, they had over 1 million users join and use this application. And that's when we talk about easy to make it scalable, easy to make your application scalable. App Engine runs for very big events like the Japanese Parliament election in 2009. We run parts of services. The EcoPoint program uses App Engine for some of the things that it does. Of course, we have a very strong community. The Japanese community here is on the Google group. We have Takashi Matsuo and Daisuke Yamashita, who kind of run the group, who are very great, excited managers, and I think we have a third manager joining pretty soon. We have some great frameworks. I've just listed 3 here that are interesting. So there's really a lot going on in the Japanese community. Now another social example here is Chilingo. They have built a social gaming platform that they make available to other developers. And they do things like game statistics and ranking. And all of that runs on App Engine. Social Walk is an application that's built its entire product on top of App Engine. So they're betting their business. I'm continuing here with the social examples. We have Gigia. They install these little gadgets in an iframe into other people's websites that make these websites social, allow people to talk to each other about an event. For example, here a movie review or maybe a sports game. And so depending on how the game happens, whether there are exciting events, maybe there's a goal, the traffic can grow and shrink very unexpectedly. So here are some of the sample traffic graphs from Gigia. And you can see that every one of them is different. It's very hard to predict what traffic's going to be like. They really can't decide how many servers they need beforehand. And even while the event's happening, they don't know when they're going to see a spike or when the traffic's going to drop off. And in fact, they try to kind of predict and tell me beforehand, oh, this will be a big event, this will be a little event. The biggest event to date was about 10 times bigger than all their other events, and it was one that they predicted to be the smallest. And that's not because they're bad at predicting, it's because it's really hard to predict. And so having App Engine allows their application to very easily scale. For DevFest, I think all of you worked on the quiz and answered some of the questions. And of course, that was an App Engine app. And I have here some of the traffic graphs from DevQuiz. And you can see that people got very busy in the weekend and kind of the week before launch, and then the traffic kind of died off again. But right before the deadline, there's a little peak. So you might ask, why did we build it? Why did we build it and allow you to use it? Well, we realized that building applications is much too difficult. I think you already know this. I mentioned configuring the operating system, the hardware, and everything. But it really should be easy. And we realized that doing your own infrastructure has a lot of hidden costs. You have licenses and patches and lots of maintenance work, a lot of hours that goes into it. So with App Engine, we give you this platform with a lot of functionality inside of a lot of APIs, infrastructure, scalability. We just make it really easy for you to focus on building the application. So that's a little bit of an introduction for those of you who are new to App Engine. Now I want to kind of switch over and talk about distributed cloud computing. We have that stack of infrastructure as a service, platform as a service, software as a service. That's just generic. That's about cloud computing. But I think App Engine is unique in that it's distributed cloud computing. It's not simply one server in the cloud or 5 servers in the cloud. Now we can have thousands of servers in the cloud, and your application can be run on those servers. And when you have more traffic, we split your application across more servers. So I want to talk about distributed computing memes. Memes, I said, are ideas or concepts. These are ways that you should think about cloud computing and think about your application so that you can really take good advantage of the platform. So I'm going to start with a summary of kind of the main themes. I won't spend too much time on this slide. There's a lot of words on here, but I want you to get an idea of kind of the things that I want to talk about. And there's really 4 points. There's making sure that you take advantage of this distributed nature so that your application is spread out, your resources are spread out, your CPU demands are spread out. The second point is that you want to be able to tolerate and expect failures. And I'll talk about what that means in a little bit. Then there's some tuning that you want to do as you get into scalability. And then the last step, just scale it up, do more. So by distributed, I mean a few things. I mean what we call divide and conquer. So we take one big task and we chop it into many tasks, and then we have different servers complete each of the tasks. That means we can do work in parallel, and we have a concept called sharding. Sharding is just like partitioning. It means what was kind of one thing, chop it into little pieces, and then later aggregate it back to it. And I have an example. I'll show you what sharding means. Amortizing work means take a task that you would do it at one time, and instead do little pieces of that work over time with each transaction. And again, I have an example of that. By tolerating it, I mean tolerate and expect failures. And then you see this word idempotency. And I put it there twice to remind you what it means. It means it is okay for the same transaction to be executed twice, or maybe 3 times, and without negative side effects. And this is important when you use, for example, task queues, but also if you try to build transactions in a distributed system. Sometimes transactions will need to be applied twice, and this allows for scalability. But it means that you have to write your code in a specific way to deal with this. So idempotency. And tune it, we do things like using memcache. All of the big applications on App Engine all make very heavy use of memcache. And even many of the smaller ones do. And those that use memcache, they see a faster application, they see less usage of their application, their users are happier, and they're happier. By tuning it, I also mean denormalization is not a bad word. We all kind of grow up in this world of relational databases. You know, we have MySQL, PostgreSQL, all the enterprise databases, and we are always taught that you should normalize your database. You should have a customer table, and then a customer address table, a customer site table, maybe a customer contact information table, maybe a customer phone number table. And each one of these tables has a primary key, and then you use joins to join all these tables together in queries. And this is just how we know how to do things. But with App Engine, we have kind of a different data model that allows it to scale up much better. And part of that is denormalizing, combining some of those things together and to create smaller entity groups. And that's really one of the keys to scaling up your data store. And finally, scale it up. That means really take advantage of the platform and kind of incorporate these themes, doing retries, making sure that your application is stateless so that each request can hit a different server and still respond. So let's start with how not to succeed, how we shouldn't do something. Let's say we want to plan a party. And so we send out invitations to all our friends, and then we check to see if everyone can come to the party. All our friends can make it. And if everyone says yes, then we have the party. That's great, we have a party. But what if one person says no, or maybe 2 people say no? Well, then we cancel the party. No party. Now, this is not a way to be successful in a social circle, because you probably won't ever have a party. You won't have any fun. Really, it's okay to have a party when not everyone shows up. You can still have fun. You can still get things done. But this is exactly how we've been doing computing for a very long time. I like to call it the monolithic computing era. That's where we think about computers as one machine. We have one desktop or maybe one server. And the way that we build these machines is we try to make them very reliable, because we only have one. You know, this is maybe our database server. Maybe this is our web server or application server. So we put in maybe 2 power supplies, and we put in extra network connections, and we put in extra CPUs and memory. And we buy very expensive memory and very expensive hard disks so that they don't fail. But we know that still things can go wrong. And so just in case, we buy an extra one, a backup. And if we get really worried, maybe we have an extra backup site. But we still have this, this is kind of like rocket science. This is how you build like a space shuttle or a rocket. You put in a very special computer that works and you've tested, and then you put in an extra one, just in case the first one doesn't work. Now this model is very expensive, it's hard to deal with, and it doesn't scale very well. So let's start looking at kind of failure rates. You know, if we have just one server, like the server, your laptop or a server desktop, every few years the server might fail. So if you just turn it on and wait, eventually after a few years the server will fail. Now if you buy a rack of servers, just because you have many of them, it's likely that on the order of every few months, one of those servers in the rack will fail. That's to be expected. And this is typical in an enterprise. Every few months, maybe every couple of years, maybe every year, something happens to the production system. There's some unexpected failure, and you encourage some downtime. That's unfortunate, but we kind of expect it. But if you start running a data center with thousands of servers in it, then you can expect that every few minutes, or maybe even every few seconds, that somewhere in the data center, something will die. There's a server that will fail, there's a hard disk that will fail, there's maybe a network router that will fail. And it's really hard to keep an entire data center running perfectly. You would need an army of people walking down the aisles, fixing things, replacing things all the time. And you probably can never do it for more than maybe a few minutes, and then something else will fail. So instead of working really hard to make the system perfect the way we used to, why not tolerate failures? Why not expect it? And if we expect those failures to happen every few minutes, and we just have lots of machines and redundancy, then our software can become much more reliable, and we can focus on doing the interesting things. And then it doesn't matter if a server dies in the data center. We just replace it with a different one. And if we get to it in the next half hour, we get to it tomorrow, that's okay. So it's much easier. Now along with this, there's this anti-pattern, this thing that we all kind of do and used to doing, which is batch processing. We have a lot of work to do, and we would like to process it. So we get a big server, and we process the work. But sometimes we have a little bit too much work. So the server takes a little bit long to run, and it starts running a little bit warm. Now that works okay for a while, but then we get a big batch job. And so we try to run that, and we buy a bigger server, but still it doesn't have enough capacity. And it takes even longer to run. There's another problem here. If this batch job takes 4 hours to run, but after 3 hours and 59 minutes, the server crashes, probably the whole batch job is lost, and we have to start over again. So it's not really good for reliability. Now if we use divide and conquer and we distribute the work, things become a lot easier. We take the batch job, we chop it in lots of little pieces, and we run them on lots of little machines, and all the work can proceed in parallel. But every once in a while, of course, we know that a machine will die or fail. But that's okay, it's a small portion of work, maybe 1 minute of work, and we just redirect it to a different machine. And it's okay, we can just continue on. So, vertical scalability really isn't scalability, because you get a server that runs hotter and hotter, and at some point you reach the limit in the capacity of that server. A better way is what we call horizontal scalability. When you need more capacity, you add more machines, and they all run nice and cool. And you can just keep adding more machines and get any kind of capacity that you want. We should do the same thing on the data store. Why try to buy a really big database to handle your task? your task might get even bigger, and then you need a bigger database and more license fees. Why not just use same pattern, horizontal scalability? Spread your data out over many disks and many machines. And it doesn't matter how many machines you have. You can store the entire internet this way. Just keep adding machines and distribute the data. And when you buy enough machines, you can store all the data. And then with an index, you can look things up. If you know the key, you can look up which machine it's on. You ask that machine, and the machine can respond. And of course, once in a while, one will fail, but that's okay. So this is what failure looks like. We have all these database servers, and each one manages a small portion of the keys, a small number of entities. And we have many web requests coming in, talking to all these different servers. But there's one that's running a little hot right here. That one is getting a little bit too much work, too many requests are coming in. And there's another one that just died. And that's too bad. So what we have is 2 failures, 2 errors, maybe 2 requests are never returned, or one of them returns with an error. If we can accept that, and our application can tolerate it, then we can use this distributed model, and we can scale the data up very easily. So distributed web hosting platform has many advantages. It's great for web applications that need a lot of scalability. We have parallel processing. It scales automatically. Distributed data store has some unique properties in that, in addition to kind of the scaling benefits, there's something unique about a distributed data store. It is that the response time for a query is not dependent on the number of entities in the data store. If I have 1,000 entities, or I have 1 million, or 10 million, or 10 billion, it doesn't matter. Because when I ask for a specific entity, I'm just talking to one server, maybe 2, and that one server responds and gives me the answer. And it doesn't matter how many entities reside on different machines and different servers, or how many other requests are coming into different machines. I'm just talking to one small database server who can answer a very simple question. What is the entity given the key that I provided? So you get predictable query performance. Suddenly, when your database size grows, you don't have to tune all your SQL queries because you get very predictable query performance. Also, because we choose an optimistic concurrency model in App Engine, there's no deadlocks. Work just continues. Even when more requests come in than the data store can handle, some requests will succeed normally in the normal amount of time. Some requests may error out, but that's again tolerating failure. Now we use the divide and conquer theme also in the design of App Engine. We have many different APIs to use, and these are kind of the most important ones represented. And each of these is located on dedicated machines. So when we want to store some data in the cache, in Memcache, we actually send the request over the network to a farm of machines that are dedicated to Memcache. That's what they do. They store things in memory and they retrieve things from memory. The data store is a set of dedicated machines that only deal with data store. The app server where your code runs is dedicated. We have front-end servers in front of that just deal with handling web requests. And by dividing the system up like this, we have very specialized systems. Each can do a task that it is dedicated to very well. And I promised you a sharding example, so this is one right here. And think of partitioning. Sharding is partitioning. And on the left side, you see a single counter. This is normally how you would create a counter. You would, every time a visitor comes to your web page, you would do a database update, and you would increment this counter by 1. The problem is when more traffic comes, the counter starts to have some contention. There's so many requests coming in to access that counter and to update it every time. So you're starting to see problems. On the right side, you see the sharded example where instead of one counter, we have 3 counters. And each request that comes in will pick one of the 3 counters randomly, or maybe it can take the IP address divided by 3. It doesn't really matter. As long as you spread the load out, you see that 2 of the requests are going to one counter, 1 request to the second one, and none to the third. So the page count that we're trying to keep track of, because every time a visitor comes, we're adding 1, is now spread out over 3 counters. We have 3 buckets. And some users will increment the first counter, some users will increment the second counter, and some users will increment the third counter. If we later want to know how many visitors we had, we have to take the count in bucket 1, bucket 2, and bucket 3 and add them together. But that's easy, right? A computer can take 3 entities from the data store and add 3 numbers together, A plus B plus C. That's pretty easy. But we get this great advantage that now we have 3 times as many counters, so we can handle 3 times the traffic at the same contention levels. And if we get even more traffic, we can just add more counters. We can have 5 counters. Maybe we'll have 10 counters. We can handle 10 times the traffic very easily. So that's what sharding is about, is taking one thing and splitting it up into little pieces. And you see, when we add even more traffic, now there's too much contention on the single counter, and it's failing, it's starting errors, there's maybe locks. But in the sharded example, things are still running pretty smoothly. So I'm going to continue with the examples here. Pre-computing values. So imagine you have a social site, and you want to see how many people are following you. So I don't know about you, but I don't have that many followers. Maybe I have 10 followers or 50 followers. So it's pretty easy to just do a select count from followers where name is my name, and I can get the result. But some people are really popular, and maybe they have 1,000 or 10,000 followers. Or maybe they have 10 million followers. And doing a select count for 10 million followers every time, that's really not the right way to go. So let's look at how that works, how we can fix that. So this is our data model. We have a user with a name, and in this case, I have 2 followers. And now a third person goes to my social website, and they click the follow button. And so what we do, of course, is we create another follower entity in the data store. Now, if that's all we did, then we would have to count these followers. Let's instead add a follower count to the user entity. And then every time we create a new follower or delete a follower, we can update the count. And now it's very easy to get that count. Even if that number is 10 million, we can just select follower count from user, and we have our answer. So here at the top you see it says amortize costs, spread out the costs. And what we've done here is, instead of, when I want to know the answer, counting all the records, 10 million records, every time one user does an update, we make a small change. We pay a small price. So this request, when a user clicks follow, 2 things happen. We create the follower, and we update the follower count. The second thing that we do takes a little bit extra time, but it's very small. And each of those extra milliseconds, they get spread out over all the requests and all the followers. And so that's amortizing costs, spreading things out. So often the case is people write an App Engine app, and they want to have a total, like the total yen amount for all orders in the system. So instead of trying to calculate that when you ask the question, you can do a little bit of the calculation every time you write an order in the data store, so that when you ask the question, the answers are already there. Now I want to refer you to another talk. This is a talk by Brett Slatkin at Google I/O in 2009. And he was, this was right before we launched the task queue capability, just about a week or so beforehand. So he talked about a lot of the features in task queues and how they work. And it's an hour-long talk, so I encourage you to look at that. But I want to highlight a few things from that. So task queues are a way to process things in the background. You take small portions of work and you put them on a queue, and then App Engine will send them back to you and process them. And if you have a lot of items to work, maybe you have 10,000 orders, and for each one you want to do something like send out an email. Then you create 10,000 tasks, and you put these 10,000 items on the queue. And App Engine will see that there's a lot of work, and so it will spin up a lot of processes to handle those requests. Up to, I think you can do like 20 requests per second per queue. And we will send the work back to you, and then your application can process these in parallel. So there's many advantages to doing background work. You can do things asynchronously, so the user doesn't have to wait. You can kind of do a big batch process and divide and conquer it into lots of smaller pieces. And it's very simple. You take some work, you put it on the queue, and then the work will come back to you. And if there's a failure, we just retry it. Now, a traditional queue kind of works like this. As an application, you put items on the queue, and then there's some kind of queue mediator, some kind of process that you can talk to. And each of the you create workers. Let's say we have 3 workers, A, B, and C. Each of those workers has to pull the queue. The worker has to ask the queue mediator, is there more work? And if the answer is yes, it gets one. If the answer is no, it sleeps for a little bit. Is there more work? And this polling takes time and execution. And that's not the best design. It makes it hard to scale because you have to assign the right number of workers beforehand. So in App Engine, we do something different. We push the work to your application. And so when you put a task on the queue, it will come back to you exactly like an HTTP request, except it's an internal HTTP request instead of an external one. And the advantage is that when you put a lot of items on the queue, we can simply spin up more event handlers to handle the work more quickly. And when there's no items on the queue, there's no processes, so there's no CPU cost. So this scales much better. It scales up, and it also scales down. So I encourage you to look at that entire talk. But Brett did another talk at the same conference, Google I/O, and he talked about something he calls relation index entities. And if you're familiar with App Engine and you've worked with the data store some, then I think you should really look at this and see if you can apply it to your application. So the talk is called Building Scalable Complex Apps on App Engine. And he's basically trying to solve this problem called fan out, where you have maybe a message that you want to send to all your followers. And maybe you have 10 followers or 10 million followers. If we copy that message to every follower, then we create a lot of data and we create a lot of work. And this is kind of how SMTP works. I send an email maybe to everyone here, and that email gets copied to every person, and everyone has a copy of it. But there's a better way of doing this, and that's only referring to the original message by a link or an index. This is really what we want. A very small piece of information, just one pointer that points back to the original message. And that's what relational entities do, or relational index entities. So we have the message. The message is the text that I send to all of you. And we use that as a parent entity. And then beneath that, we create child entities called message index. And we create one for each recipient of the message. So each one of you will have a message index, message index value. And so what it looks like in Python is this. We have a message class, we have the sender, that's me, and the message body, that's the text I typed going to you. And then the message index class looks like this. In one entity, instead of just putting one value, we actually put a list of values. So I can put up to 1,000 values. So actually all of you would fit in one of these entities. I just need one value, one ID for each person that is receiving my message. But if I have 5,000 followers, then I could use maybe 5 index entities. So that's exactly what we do. We just create more index entities. Now, if you look at Brett's talk in detail, you actually see that there's some more tricks behind the scenes here. Because it's parent and child entities, we can use key prefixes, and we can avoid some database lookups. And this is a really efficient technique to solve this fan-out problem. So it's too much time to spend on it here, but if you're interested in this, definitely look at it. Now, one more example from that talk was querying the social graph. We have some friends. We have Bob and Mel, who live in New York. We have Stu and Willie, who live in San Francisco. And we have Lenny and Carl, who live in Chicago. And we have a problem. We want to find out who are the mutual friends of Bob and Willie in San Francisco. Who are the people that know Bob and know Willie and live in San Francisco? So let's look at that. We have, this is actually the query that we can write. We have a person class that contains location and friends. Both of those are indexed. And we have a SQL query. We say select from person where friends is Bob and friends is Willie, and location is San Francisco. And you see, this is a little different than SQL because we say friends equals :1 and friends equals :2. And they're two different values. And what this really means is you should read that as friends in, or sorry, as :1 in friends and :2 in friends. Because friends is a list property. It contains many values. Maybe I have 10 friends, so it has 10 values. And this means, does friends list contain both Bob and contain Willie? So here we have that social graph, and here's our location index. And we have in there, this is all in alphabetical order. You see C for Chicago first, N for New York, S for San Francisco. And then we have a friend index, B for Bob first, same thing. At the very bottom, W for Willie, so alphabetical order. And we do what's called a merge join. This is a special join query that App Engine supports. And we put a pointer on the location, the first location, San Francisco. We put a pointer on the first friend, Bob, and another one for the first friend, Willie. And then we look at the keys, and we find the key that has the highest value. So we see we have Stu, Mel, and Lenny. Now, S for Stu is the last one. So we're going to start there. And we update the pointer to the next one, and we see that we have a match, Stu. Then we update the pointer to the last one, and again, we have a match. We now have a three-way match. And that is how the merge join works. And this is distributed. So the pointers 1, 2, and 3 might be on different servers in different part of the database, but they can together work to create the result of this merge join query. So I just want to now wrap up and hope you see those talks online. So App Engine is very much an evolving platform. Almost every month we release some major features so far. Since we launched originally in April of 2008 with the Python language, then a year later with Java, you can see in the calendar that we launched a lot of very important features, and we hope to continue this path of innovation. So if App Engine doesn't do exactly what you want today, I encourage you to check back in a short amount of time. We, of course, have a roadmap online where you can see the things that we're working on next. And if you want to learn about App Engine, there's a code lab created by GTUG. And, I told you, App Engine, we try to make it easy to build, easy to maintain, and easy to scale. Well, with this Code Lab, it's also easy to learn. So with that, I want to thank you very much. Now we're out of time here, but I do want to answer questions. So I'll be out in the hallways, answer me questions. I also brought business cards, and you can take my email address and ask me a question later. And also join the App Engine Japan community, very active community, and participate. Thank you.